We want to start this section by graphing some inequalities. The first one I've written here is x minus 2 squared plus y plus 3 squared is less than 16. So you can see it's an inequality that's nonlinear. I'm going to use the same methods I've used in the past by first graphing the boundary. So the boundary is going to be what I get when I replace the inequality symbol with an equal sign. So it's going to be x minus 2 quantity squared plus y plus 3 quantity squared equals 16. And when I graph this, since this original inequality is a strictly less than symbol, this is going to be a dotted curve. So let's graph this. This is a circle with a center at 2, negative 3. So x equal 2. Let's just see here. X equal 2, y equal negative 3. That's going to be the center of the circle, and it has a radius of 4. So let's see. I'll go up here, back this way, over here. I'm just going to estimate this and see what I can get. Okay, I'm going to draw in this circle now using a dotted curve. Well, it's a pretty good circle. So that's the equation of the boundary for this graph right here. So the graph of this equation is going to have this dotted blue circle right here. You have to imagine that it's a circle as its boundary. Now what I need to do next is to check some point that's not on the boundary in the original equation. Well, let's check the coordinates in the original inequality, I should say. Let's check the coordinates of this center, which is at 2, negative 3. So I'm going to check, or test, I should say. Let's test the point x equal 2, y equal negative 3 in my original inequality. When I do that, I get 0 squared plus 0 squared less than 16. 0 less than 16, that's a true statement, which means that my test point lies in the region of the solution set. Here's my test point here in the center of this circle. It is in the solution set, so all the points that lie in the center of the circle right here are also part of the solution set. So I'll just color everything in the center in. So this inequality right here specifies the inside of this circle. The boundary is a dotted line, so it's not part of the solution set. The solution set lies within that circle. It's all the points that lie within the circle. So you can see that graphing these inequalities, these nonlinear inequalities, proceed in much the same manner as we use to graph linear equations in two variables. Linear equations in two variables. Let's look at the next example. Let's see if I can do a little better job with this. Okay, this is going to be a system of inequalities. Now let's look at the boundaries over here. Okay, the boundaries are going to be x squared plus y squared is equal to 9. And it's going to be dotted. So let's graph this inequality first. That's a circle with a center at the origin and a radius of 3. So let's just call this 3. And I'll draw in a dotted circle, which looks like this. And that's x equal 3. Now, I'll test the origin. It's not on the boundary right here. 0 plus 0 less than 9. Is that a true statement? The answer is yes. So I'm going to color in the circle on the inside here like this. All right, let's go to our second inequality. It has a boundary. Let me just erase this right here, okay? This is going to be, I just want y here instead of y to the second power. I copied this problem wrong. Anyways, it's y is greater than or equal to x squared minus 1. That boundary is going to be y equal x squared minus 1, and I'm going to graph it with a solid line. Now, y equal x squared minus 1, when x is 0, y is negative 1, so it goes through the y-axis right here. It's a parabola, so if I go over 1 and up 1, I'm back on the curve, over 2, I'm going to go up to 3, so I'm going to be up here and here. Anyways, this graph is going to look like this. Okay, that's the boundary. I've drawn it with a solid curve. Now I want to test some point that's not on the boundary. Again, the origin is not on the boundary, so let's test 0, 0 in the original inequality. 0 greater than or equal to 0 squared minus 1. Is 0 greater than or equal to negative 1? The answer is yes. So I'm in the correct region when I'm here at the origin. So the graph for this inequality right here lies inside this parabola. So that's going to be this. Now, when I want to graph the solution to this system of inequalities, what I want is all the points that do this and also do this. So where is that on my curve? Let's take a look. Or where is that in these regions right here? Everything that's inside this little part right here. So it's dotted here, it's solid down here, and then it's everything inside. So everything inside this little region right here is a solution to this system of nonlinear inequalities in two variables. I have this graph, which is a certain section of the coordinate plane inside this circle, this graph right here, which is inside the parabola. I want all the points that are in both places, that is both inside the circle and inside the parabola. That's this little section right here. Now, next what I want to do is solve some systems of nonlinear equations. So this is a system of equations instead of inequalities. So I'm just going to get ordered pairs, maybe 2 or 3 or whatever, that are solutions to both of these equations right here. But let's take a quick look at the graph just to see what we're dealing with. X squared plus y squared equals 9. That's the equation of a circle, center at the origin, radius of 3. So I'm just going to draw a circle in real quick and call this 3. My second equation, 2x plus y equals 3, that's the equation of a straight line. When x is equal to 0, y is equal to 3. So I get this point. When y is equal to 0, x is equal to 3 halves. That's going to be somewhere around here. So I get a straight line that looks like this. Well, I should have two solutions to this system. This point right here, which is x equals 0, y equals 3, and then this point right here. So to find the coordinates of this point, I'm going to have to solve this system right here algebraically. So let's do that. I'm going to have to use substitution here because I have different powers of x and y in this equation than I do in this equation. So let's take this equation right here and solve for y. If I do that, I get y is equal to 3 minus 2x when I add negative 2x to both sides. Now I'll take this expression for y and substitute it into my second equation in place of the variable y. And so I get x squared plus 3 minus 2x, quantity squared, is equal to 9. Okay, let's solve this equation. X squared plus, okay, I got to square this binomial, 9 minus 3 times 2 is 6, doubled is 12, x plus 4, x squared is equal to 9. 1x squared plus 4x squared is 5x squared, minus 12x, and then I'll add negative 9 to both sides, so I end up with 0. Factor x out of these two terms, and I have x times 5x minus 12 is equal to 0. That tells me that x is equal to 0, or 5x minus 12 is equal to 0, which means that x is 12/5. So here are the x coordinates of my 2 points of intersection. X equals 0, and sure enough, that's that point right here. And then x equals 12/5, which is the x coordinate of this point right here. Now, to find the corresponding y coordinates, I'll substitute this value of x and this value of x separately back into any one of these equations. Since we're looking for y, let's take this equation right here. When I substitute x equals 0 into 3 minus 2x, I end up with y is equal to 3. Well, of course, that makes sense because that's one of the points that I have. Let's substitute in x equals 12/5. I get y is equal to 3 minus 2 times 12/5. Now I'll multiply through by 2 here. I get 3 minus 24/5. That's 15 over 5 minus 24 over 5. And that should be negative 9/5. That's my value of y. Here's this value of y. I end up with two solutions. X is equal to 0, y is equal to 3, and x is equal to 12/5. Y is equal to negative 9/5. So the coordinates of that sort of mystery point that we had when we graphed these, this point right here, its coordinates turn out to be 12/5 and negative 9/5. So in fact, when I solve this system algebraically using substitution, I end up with two ordered pairs that are solutions, and that information is consistent with the information that I got over here when I graphed the two equations to begin with.